go ahead and get started. Now, I really wanted to cover nomenclature last week, and we didn't get to it. And I think that we could have crammed it in there, but the question that was on the unit test that asked you about spectroscopy, I felt like it was easy enough that if you remembered your basics from OChem 1, you really weren't going to struggle. There was a typo on one of them. So I'll go through and make sure that everybody got points for that problem that should have gotten points. Caesar? You got a 0 on the nomenclature one? Did you submit it after 6 p.m. last night? Okay, that's it. Good. Yeah, you. I'll have to go in. I don't know why it automatically shows as a 0 instead of a blank. That is a little disconcerting, isn't it? Good. All right. So we're going to dive into section 15, finally cover some new material. And one of the benefits of not covering nomenclature last week is that I can cover it today and use it as a segue into the nomenclature of aromatic compounds. So we'll do kind of a nomenclature review, segue it into nomenclature of aromatic rings. Now, I'm not sure how each of you were taught nomenclature in OChem 1, but I'll give you kind of a framework of how nomenclature is often taught. Textbooks will sometimes give a big picture idea of what nomenclature will look like, but oftentimes textbooks will just introduce you to nomenclature as it applies to each functional group as you learn about that functional group. So how many of you know how to name a ketone? How do you name a molecule with a ketone? Anybody learn that? No. It's not any more challenging than learning how to name an alkene. How many of you learned how to name an alkene? Right. So there's a lot of nomenclature that you learn bit by bit by bit that applies to every other functional group as well. Most of your nomenclature will be broken down into these parts: the prefix, the root, the locant, and the suffix. And we're going to talk about each of these parts, but not necessarily in that order. The main part of a molecule's name comes from the root, locant, and suffix. This is where you get the information about the parent chain and the primary functional group and where along the parent chain that primary functional group exists. But the prefix looks like it's a small part of the name, but oftentimes this is what makes a name so long and cumbersome. So let's start with our roots, because this is ideally the first thing that we identify. The root indicates the number of carbons in the longest chain. It indicates your carbon chain length. And there are a lot of different ways that you can choose your carbon chain length. Ideally, this is your parent chain, which has the longest carbon chain plus a primary functional group. Okay, then I think in order to figure out how to find the root, we have to figure out what are the primary functional groups. And I understand that in OChem 1, you rarely talk about reactions with carboxylic acids, or esters, or anhydrides, or amides. But there's no reason that that has to be hidden knowledge, that those are a series of primary functional groups. I'm not sure exactly why IUPAC prioritizes functional groups in this sequence. They just have. And we're actually not going to look at all of them. But we're going to look at the ones that we'll come across this semester, the ones that are of most important to us. The highest priority functional group is a carboxylic acid. When a carboxylic acid exists in a molecule, that's where you start numbering. That's how you prioritize the parent chain. After carboxylic acids come esters. You'll notice actually that this series begins with a lot of carbonyl functional groups. We're going to focus mostly on having carboxylic acids and esters in our nomenclature this semester. After our functional groups that have carbonyls, we move down to our lower priority functional groups, the top of which is the alcohol. By the way, I just want to reference for you guys where you can find this information. I've linked this free textbook on our homepage, the McMurray textbook. If you come all the way down here to Nomenclature of Polyfunctional Organic Compounds, that's, I think, Appendix A. It lists all of your different functional groups alphabetically. And then here, it prioritizes them. You'll see that I skipped over acid anhydrides. We're going to learn how to name these, but we're just not going to see them as a priority group, so we're not going to have to rank them. And then esters, amides are in there, and nitriles. I did skip a couple. I'm sorry. I wanted to make sure I didn't skip those. That's why I wanted to pull this up. I'm going to erase alcohols. So we're going to squeeze a couple more in there.
Is there a difference between acid anhydrides and regular anhydrides? Or is it the same thing?
It is the same thing. Yeah, anhydride is kind of a shorthand way for saying acid anhydride. I guess it'd be kind of like saying if we referred to carboxylic acids as just acids, if we knew that that's what we were talking about. But acid anhydrides form, well, they are considered the carboxylic acid, two equivalents, bonded together, less a molecule of water. So they're acid without water, anhydride. Okay, carbonyl groups. After carboxylic acids and esters, we're going to see aldehydes and ketones. And here's how I'm going to order this. I'm going to say that aldehydes are greater than or equal to in priority with ketones, which is to say that if a carboxylic acid and an aldehyde are in a molecule, carboxylic acid wins. If carboxylic acid and a ketone are in the molecule, carboxylic acid wins. But if an aldehyde and a ketone are both in the molecule, the aldehyde wins. And there is a good reason for that. Aldehydes are terminal functional groups. So a carbon chain will always start at an aldehyde. And then you can number from that aldehyde towards where the ketone is. So if you have both of these functional groups, start at the end of the molecule and then move inward. After our aldehydes and ketones, then we see our alcohols. I think it's funny that they put phenols after alcohols because a lot of times phenols are just considered alcohols. After alcohols, we won't We won't be doing a lot of naming with amines. We won't be doing a lot of naming with ethers. So then afterwards, we'll look at our alkenes, which are equal to or greater than in priority to alkynes. And what's the idea here? Why is an alkene equal to or greater than an alkyne's priority? It's to say that if both an alkene and an alkyne are present in the carbon chain, you prioritize giving the alkene its lowest locant first. Why would you prioritize that over the alkyne? Because IUPAC says so. IUPAC had a pretty good reason for saying why aldehydes should come before ketones, because now you can start numbering from the end of a chain, and you make sure that the aldehyde gets the lowest locant set possible. Why would an alkene make more sense to be higher priority than an alkyne? Comes first, alphabetically. You're going to see in the suffix "ine," "ein." So prioritize the alkene. The only reason that you would need to distinguish between these two is if you number from different sides of the chain and they get the same locant. Number from the left-hand side and the alkene gets locant 2. Number from the right-hand side, the alkyne gets locant 2. Which way should I number? My locant set is the same. Well, I'm going to number it in such a way that the first alphabetically gets its lowest locant, since the name is organized alphabetically. This is why we prioritize our alkenes over alkynes. Then you can see that the lower priority groups are the alkyl groups and the halo groups and the nitro groups, but we're not going to do a lot of nomenclature with nitro groups. And here I'm saying that these are identical to each other. You would prioritize one over the other if there was a tie and you go alphabetically. But otherwise, methyl, ethyl, propyl, butyl, sec butyl, tert butyl, they all have the same priority as fluoro, chloro, bromo, iodo. There's no difference in priority. You just look for the lowest locant set and you alphabetize them. And then you, if there's a tie, you prioritize alphabetical. Now, we need to get back to roots to talk about carbon chain lengths. We're going to use these prefix terms, meth, eth, prop, but. I always forget if it's Greek or Latin prefixes. I don't speak either of those languages, so it's hard for me to remember them. Now, we're not going to look at very long molecules this semester, so I'm not worried about us recognizing root lengths past 10. I suspect we won't see many root lengths past 8. But a 1-carbon root is given meth, 2-carbon eth. All the way through prop and but for 3 and 4, I feel like these prefixes are the most unique to organic chemistry nomenclature. And then after we get through the rest, the prefixes start to look a lot more like what you learn in geometry and math classes. So what is the root for 5? Pent. For 6? Hex. As opposed to sext, which I think is the Latin. Hex, I think, is the Greek. So going back to that, I think we're in the Greek. 7? Hept, as opposed to sept. So there's that difference. The other prefix nomenclature is sext and sept, but in Greek we're doing hex and hept. 8, oct, 9, known or non, 10, dec. Awesome. You'll notice that the roots don't have anything coming after them. That's where our suffixes come into play. We're actually going to use these roots again in our prefixes when we have carbon chains that branch off of the parent chain. So we'll have different types of suffixes that we can put here. We'll be able to put ein, ein. We'll be able to put OL for alcohols, oic acids for carboxylic acids. But we'll also be able to put YL, which makes methyl, pentyl, heptyl, and that allows us to take a carbon chain and describe it as a substituent of a root parent chain, rather than its own chain on its own. Okay, so far so good. Awesome. Then let's move. You know what? There's a document that I've been trying to make that it is not really fleshed out yet, but it is it's something I've been trying to make to help people go through nomenclature one step at a time, especially early on. The premise is that you can't understand the nomenclature of sorbitol and Freon 112 by those names. But if you understand the IUPAC nomenclature, you can get it. So I've got this kind of worksheet that tries to go through it. Yeah, actually, I'm glad I pulled this up because there is something important for us to talk about, which is the cycloroots. Cyclo is not necessarily a prefix to the root so much as it is a descriptor of the root itself. When you've got a cyclic chain, you still describe it by these roots, but you have to emphasize that it's a cyclic chain rather than linear. We just add cyclo. So how many carbons in this cyclo-oct ring? 8. How many carbons in this cyclohept ring? What would we give the prefix or the root for this 6-membered ring? Cyclohex. For a 5-membered ring? Cyclobute, or cyclopent, excuse me. Here we've got our 4-membered cyclobute, which would take what shape?
Square.
Just a square. Cycloprop takes what shape? Little triangle. Great. And then here, this is where it kind of transitions into roots. I've got this 1 carbon chain, and that's kind of what fills in here. Or if I've got a 3 carbon chain, then I know I'm going to have 3 lines. If I've got this 8 carbon chain, then I can start to figure out how the prefix combines. It's not fleshed out well. I might pull it up as we continue talking about it. All right, let's move on from root to suffix. Now, the general idea is that the suffix indicates the highest priority functional group. So carboxylic acids, they get emphasized at the suffix. anything else would have to show up then as a substituent at the prefix. But there are ways for multiple functional groups to appear in the suffix. Generally, a name will actually contain the suffix that applies to a hydrocarbon functional group, and then that suffix will be modified or stoppered by a different suffix that indicates these heteroatom functional groups. So I'm going to introduce something that's not just suffix. This is often for hydrocarbon groups. And those suffixes that we learned for hydrocarbon groups, alkane gives us the suffix ane. Alkene gives us the suffix ene. Alkyne gives us the suffix ine. But also, when alkene and alkynes are present in a molecule, then you can have the suffix ene, ine. Have you guys seen a name like that before? If they're both in the longest parent chain, then they both end up in the suffix. But you will never see ane combined with ene combined with ine, or ane combined with ene. And that's, I think, because a lot of people don't even consider alkane to be a true functional group. So as soon as a higher order hydrocarbon group comes in, it takes the suffix. Then we get suffix stoppers or suffix modifiers. I like suffix stoppers because it's an alliteration. Although the first time I started teaching this, it was such a tongue twister. I kept saying stuffing stoppers. It was right around Thanksgiving too. Suffix stoppers modify the ane, ene, ine, or ene-ine to indicate a heteroatom functional group. And this is where rarely would you see multiple stoppers. But you will be able to see ene with a stopper, ine with a stopper, and ene-ine with a stopper. So let's go through them for the ones that we've already covered. Carboxylic acid gets the suffix stopper oic acid. Which is to say that you would never have butoic acid. You'd have butanoic acid, where actually the E of ane gets replaced by oic acid. Or you could have 2-butenoic acid, where the second E of ene gets replaced by oic acid. We'll look at some examples for these two. Esters. Esters get the suffix stopper -08. We'll look at these nomenclatures again in a later chapter, and we'll find out that -08 also is the suffix for carboxylates, the conjugate base of carboxylic acids. Aldehydes are given the stopper Al. You can see that Al indicates the aldehyde by just being the first two letters of the functional group. In my opinion, esters, they're the ones with the suffix that connects the least to the molecule itself. Ketones. Do you guys know what suffix these get? What? One. Yep. O-N-E. which clarifies the compound as a ketone because you hear "one" at the end of ketone, "one" at the end of the name. And you can actually hear some of these nomenclature pieces come up in molecules that you guys know about, like testosterone has a ketone in it. You guys all right if I erase this part of the board and make some more space? All right, now here is something that I know you guys know, which is the suffix for alcohols. Oh, I thought you knew it. All, O-L. Hard to distinguish verbally from all for aldehyde. So when it comes down to it, I'll try to emphasize the distinction between them. We're not going to see any suffix stoppers, of course, for alkenes, alkynes, alkyls, or our halo groups. So let's apply what we've got so far to some of our molecules, shall we? Yeah, it's an okay start. We're starting off easy. I hope it feels easy. Let's start by looking at the molecule on the top left. What root is that name, is that molecule given? Not meth. F. Yep, sorry. Given the root F, what suffix and or suffix stopper will this compound get? It won't get "ene." It will get "ane" because there is no alkene or alkyne, stoppered by oic acid. So instead of ethoic acid, this is ethanoic acid. So here's my root, suffix, suffix stopper. Yeah? This molecule goes by another name, by the way, a common name. Do you guys know this molecule? I bet you've been learning about it since Gen Chem. This is acetic acid, and we're going to run into this common piece of nomenclature, the acetyl group, quite a bit this semester. And the acetyl group basically means I have a carbonyl with a CH3. So there is a lot of common names in nomenclature. I don't like common names because they don't allow you to predict structure quite as well. Like ibuprofen. Do you know that ibuprofen has an isobutyl group? And you can hear it in the ibu. And it has a benzene ring, and you can hear that in the phene, like phenyl. And it has a, I don't think it has an alkene. I don't know what the ene comes from. Ibuprofen, right? The phenyl ring. I don't like it. I don't like common names. I think that it kind of steals from us being able to communicate. Acetic acid is something that everybody knows. It's a part of vinegar. But ethanoic acid, you don't have to guess. 2-carbon root with an alkane and a carboxylic acid functional group. All right, what root do I give to this compound? This gets bute. No. Pro. What suffix and suffix stopper will it get? Ene and al. because it has both an alkene carbon chain and an aldehyde primary functional group. So 3-carbon chain with an alkene and an aldehyde propanol. Now I haven't actually gotten us to the locant part, and because this molecule is so small, there's no way that the alkene and the aldehyde could be in here any other way, so I don't need locants. But in a longer carbon chain, I might need to start saying this is a propene or maybe a pentene or maybe a hexene chain with the alkene at a specific position. And then I'd have to add a locant to designate where that is. Let's move straight down. What root do I give this? Prop again. Suffix and suffix stopper. Alkane and for ketone, one, which gives me anone. Propanone. You're right, this is acetone. And what do you notice in the name acetone? This little acetyl part of the name again, kind of indicating this carbonyl with a CH3, and in this case, it's a ketone version of that acetyl group. I don't like it, but I'm pretty sure that's how it got its name. You'd never be able to derive its structure from the name acetone. It doesn't give you that kind of information. Propanone does. Now, in talking about locants, I don't have to add a locant here that describes where my ketone is. You'll notice if you look up this version of acetone's name, it often does come up. But if I move this ketone to either other carbon, it stops being a ketone. It starts being an aldehyde. So there really is only one structural form of propanone. All right, how about this compound? What's the root? Not just hex? Nice, cyclohex. What's the suffix that it will get?
Anone.
Yeah, it's going to get AN for the alkane part of the ring and OL for the alcohol that's on there, cyclohexanol.
You also call it alcohol, since the alcohol is the...
Actually, Caesar, what you're getting at is something called functional class nomenclature, where you name the whole carbon chain as a substituent of the functional group. So this could be called cyclohexyl alcohol. This could be called dimethyl ketone, which is methyl-methyl ketone. This could be called, I think you'd call it ethyl carboxylic acid. You might actually just call it methyl carboxylic acid because carboxylic acid already implies one of those. There are some molecules that we would prefer to name it by its functional class. Diethyl ether is a really common organic solvent. We use it in the labs a lot. Diethyl ether is a functional class name, and its IUPAC name would be ethoxyethane, which just doesn't roll off the tongue as well as diethyl ether. So there is, there's some give and take with when you want to do functional class and when you want to do IUPAC. Is that good kind of exposure, early exposure to tying in the roots and the suffixes?
What
Caitlin?
about if there's like two functional groups on one molecule? I know it's like has to do with priority, but is it like the highest priority one ends up at the very end, or it's like?
Yes, we'll talk about that. By the time we get to prefix, that's where we'll talk about how to get them both in there. First, I want to give a perspective on locants. Locants are used actually to describe where functional groups or substituents are located. And those substituents are things that will show up in the prefix. The molecules that I gave you here, I intentionally avoided needing to have locants. But now let's take an example. One important thing to say is that we prioritize the lowest locant set. Something that you could add here is for the highest priority functional group. When you have a carboxylic acid, you're going to start by making that carbon-carbon one. But if you have an alcohol and it's somewhere along the carbon chain, you're going to number the carbon chain in such a way that that alcohol gets its lowest locant. And then everything else will fall in place. And if there is no highest priority functional group, then you just prioritize getting the lowest locant set total. So let's look at a couple of molecules. And let's use locants as we need to name them. What is the root that I'll give to my first compound?
Hex.
I agree. Hex. So this first compound is going to be hex something. Which way should I start numbering it? From the left or from the right? That's not the best question to start with. The best question to start with is, what is my highest priority functional group in this molecule? Alcohol is my highest priority. Now, which way should I start numbering so that the alcohol gets its lowest locant? From the right. I think you guys would agree that's going to place the alcohol on position 2 rather than placing the alcohol on position 5. But it's going to place the alkyne on position 5 rather than placing the alkyne on position 1. Turns out, I don't care. I don't care what the alkyne could or could not have been. I care about the alcohol. That's my highest priority functional group. So I'm just going to number it so that we can see these locant positions. Now this is going to become hexyne-ol, but I need to describe exactly where the alkyne is and exactly where the alcohol is. So this is hex 5-ine 2-ol. I cannot assume to know that the alkyne starts on position 5 and connects to position 6. I cannot assume to know that the alcohol is on position 2. There's no way I could know that. It could have been 1-ol, 3-ol, etc. I also don't have to number both carbons of the alkyne in the locant. I just say where the alkyne starts, and then it's assumed that we know where it goes to. Now, carboxylic acids and aldehydes, those functional groups are terminal, which means you never have to give a locant for a carboxylic acid or an aldehyde. It's assumed that we know where they are. But ketones and alcohols are unique because ketones and alcohols could move along a carbon chain, so we generally have to give their locant except if there's a ring. Because where do you start numbering in a ring if not right at the primary functional group? So then I don't need to describe that the primary functional group is being named there. So 1, 2, this gets the root cyclohex. It has an alkene that starts at position 2 relative to the ketone, So this is cyclohex 2-ene-one. And I could say cyclohex 2-ene-one-one. That would do just fine. Because I could clarify that the ketone is at position 1, but where else would it be? Because I'm in a ring, I'm going to start numbering at the ketone. Now you guys will notice that I've been putting the locants kind of within the nomenclature, after the root. This is actually what IUPAC says is correct. But for any one locant, you can place it before the root as well. So this molecule could have been called 5-hexyne-2-ol. I can't call it 5,2-hexyne-ol, but I can call it 5-hexyne-2-ol. And down here, I could call this 2-cyclohexene-one. I can really only take whatever first locant is going to be in the name, and I can pull that in front of the root, which makes it convenient here. All right, before I get too far into the prefixes, I want to add something about locants, which is when you have multiple of them, multiple functional groups that are changing the suffix and need to have their own locants. The way that we write things can show up differently, but this is not one of my major priorities. So this compound would best be called, oh no, I'm gonna modify this. Yeah, it's just gonna be a 5-membered ring. Cyclopent. And then I've got 2 alcohols, which actually means that I'm gonna have to describe the suffix as not just OL for alcohol, but diol. I'm going to have to change the suffix to have a multiplier in it. And because of that, instead of modifying ane to be just AN, and the E gets dropped and replaced by OL, it's going to come back to ane, and then I'll have 1,2-diol. I'm not a big fan of that, but that's what they do. They put the E back in. Cyclopentane 1,2-diol. So 2 things I want to point out. This is a multiplier. And we use di, tri, tetra, etc. I doubt that in our class we'll ever come across more than tetra. And then the other thing that I want to point out is the 1,2. Each group gets a locant. So for every multiplier that you see, there should be a locant listed for it. Here's an instance that is very similar that people think I don't need to list multiple multipliers. So people will take this compound, cyclopentane, and they'll name it as 1-diol. Cyclopentane 1-diol is not correct. You've only listed 1 locant, but you're saying that there are 2 groups. Diol, 2 alcohols, needs to have 2 locants. Now what the student is thinking is, both of those alcohols are on position 1. Why would I need to say that they're both on position 1? Because what if I think that you forgot the second locant? What if it was 1,2 or 1,3 and you just didn't think to put it in there? So clarify, make it as clear as possible. This is 1,1-diol. There can be no confusion about where those 2 alcohols show up. You guys okay with that? Great. Okay. Let's move on to the prefixes because this is the fun part. Prefixes show all other carbon chains and functional groups not already indicated by the root or suffix. And we had this question, which was, what if I have both a carboxylic acid in my molecule and an alcohol? How do I know that the alcohol is there? So some functional groups can actually end up becoming suffixes, or excuse me, some functional groups can end up becoming substituents represented in the prefix rather than being represented in the suffix. I'd rather not go over what we'd call it for carboxylic acids and esters, because what we'll see the most are the suffixes for aldehydes, the prefixes for aldehydes and ketones. These are given the prefix substituent term oxo. And they're both given that prefix term. So if they cannot be designated in the suffix, then they're designated as a substituent by the term oxo. I said aldehydes already. Alcohols become hydroxy groups. And there are prefix terms for some common alkenes and alkynes. We're not going to see those this semester, so I think that I'm going to just limit us to this. This is primarily what we want to look at. But then we've got our carbon chains. For any carbon chain, you just take its root and give it a suffix YL. That gives us methyl, ethyl. I'm going to skip a few and get to some fun ones. We've got things like tert-butyl, T-butyl.
Are we gonna see stuff with sulfur, like sulfites?
Not much. Definitely not with nomenclature. Yeah. So generally what I do for my class is recognize that a lot of molecules are no more challenging to name than the ones that we're going to cover. They're just less common or not as ingrained in the reactions that we're going to do. So I'm not skipping any of these functional groups because they're just needlessly hard, just because we're not going to cover them. So I'd rather not spend the time on it. There's another one I think we'll see quite a bit, which is the isopropyl group. But I think you guys can agree we'd have propyl, butyl. There's also sec-butyl and isobutyl. These are some of the most common ones. So that little suffix YL, it gets added to the roots to say this is not a primary chain. This is not a parent chain. This is a substituent chain. This is just a group. So let's just round this out with a couple more names. Okay, what is the root that my first compound gets?
And
Pent. Any prefixes that will come in this compound?
hydroxy.
Yeah, hydroxy is not going to show up in the suffix because the carboxylic acid is going to claim the suffix. So I'm going to number this from my carboxylic acid to my hydroxy group. That gives me 4-hydroxy pent. I have an alkene that starts at 2, so that's 4-hydroxy pent 2-ene oic acid. Not a very big molecule, but its name can take up a lot of space, can't it? How about this next structure? What is the root that I'll have?
X.
This one gets hex. Which way am I going to start numbering it? From the left or from the right? I've got a ketone functional group and an aldehyde. Which one is priority? Aldehyde. So I'll number from the aldehyde. And you guys can see there's that benefit. My aldehyde is going to be at position 1. I won't even need to say the locant position for my aldehyde because it's always going to be at the end of the chain. What will show up in my prefix? Methyl and oxo. Which one shows up first? LMNO. M comes before O, and we always organize this alphabetically. So this will be 5-methyl, 4-oxo, hexanal. Can someone remind me, why am I not doing 4, 5 hexanal? Do we always list our locants from highest number to lowest number? That's totally random. It all depends on the alphabetical order of the groups themselves. Methyl comes before oxo, so I've got 5-methyl, 4-oxo, hexanal. All right? Now this one is a little bit more challenging in terms of what locants should be given what. So, what is the root and suffix for that last compound? Cyclohexane. Which means that these two groups are going to show up in the prefix. Bromo and tert-butyl. Which one shows up first?
Bromo.
Why?
Halogen.
Halogens and alkyl groups are of equal priority.
Yeah. Alphabetical order.
So bromo comes before. What part of bromo is beating out what part of tert-butyl?
The B and then T.
Good, I'm glad you said that. The T is not alphabetized. Only the B is. And then we have things like isopropyl groups or isobutyl groups where the I is alphabetized. It is a strange thing. Isobutyl, isopropyl, that's a common name, so it gets alphabetized by I. Sacbutyl and tert-butyl is actually a descriptive name. It describes how the carbon attaches, so it's not part of how it gets alphabetized. So I'm looking at bromo versus butyl, even though it's going to go in the name as tert-butyl. So what wins out bromo or butyl? B and B are tied. Now it's just R and U. LMNOP, QRST. Okay, so bromo does win, but not because it's a halogen and not because B beats out T. Bromine goes first because R is first alphabetically compared to U. Now, I could have numbered this 1 bromo, 3 tert-butyl, or 3 bromo, 1 tert-butyl. It's a tie in either direction. So how do I decide whether to name it from bromine to terbutyl or from terbutyl to bromine?
Shortest way.
When there's a tie, what'd you say?
The shortest way.
The shortest way is a tie.
Oh.
1, 2, 3, 1, 2, 3. I could go either direction and it's 1 and 3. When it's a tie, you give the first alphabetically its lowest locant. It's just a good way to win a tie. So 1 bromo, 3 tert butyl, cyclohexane. In my opinion, it's the OChem 1 nomenclature that's actually a lot harder than the OChem 2 nomenclature with those other functional groups. It gets a little bit more complicated with suffixes and suffix stoppers and all the locants, but at least you normally don't have to beat out a tie like that, you know. All right, guys, I want to give you guys a quick break because you've been looking at weird language for the last hour. So why don't you get up and move around for 3 or 4 minutes, get your blood flowing, come back in, and we'll talk about naming aromatic rings. There are some weird things in nomenclature. I don't like to get them this complicated, but you can see like molecule 4 has both a carboxylic acid and an amide in its structure, and the amide becomes a substituent, carbamoyl, right? So this OYL is a suffix. The carb is saying there's 1 carbon, and then the AM is saying it's part of an amide. So it's a carb amide, but it's not a carbamide. That's a suffix. Instead, it's a carbamoyl substituent. Good. One thing that you'd notice is the root pentanoic 1, 2, 3, 4, 5 doesn't include the carbon of the amide, even though that is connected linearly in the carbon chain. But that's because how else will I name the amide as a substituent unless I name the carbon of the amide as well? We're not going to get that deep. That's a lot more in depth than what, not because it's impossible, just because I would rather have you guys really strengthen your foundational skills than like stretch yourself to do these wild ones. But then you see this molecule 5, and the root of the molecule is cyclohexane carbaldehyde. Because you'll notice that the highest priority group is the aldehyde, but that aldehyde is not attached within the ring. So how do you name the carbon of the aldehyde when it can't be part of this cyclohex? It gets named here, carb aldehyde. And then you've got the oxos.
So I was confused with like the functional naming, because when you can't, it's not part of the longest carbon chain. I thought, if this is the highest functional group, you would name it like a functional
So this is not functional nomenclature.
Right, that's
It's still IUPAC, but it looks more like functional
I
nomenclature.
mean, yeah, because the highest function is still going to be the aldehyde.
Mm-hmm. One thing that you can always bank on with functional class nomenclature is that you'll see two separate words. So cyclohexyl alcohol, 2 words, or dimethyl ketone, 2 words. So if this was functional class, then aldehyde would have been on its own. Now, this does surprise me because my intuition looking at this molecule would not be to make the ring and the aldehyde coming off of it all the parent chain. My intuition would have been make the ring the parent chain and make the aldehyde a substituent coming off of this. I would have called this molecule 3-carbaldehyde cyclohexanone.
Well, wasn't one of the rules that you have to name the parent chain based on where the highest priority group is?
Correct. But ketones and aldehydes are the same priority.
Oh, yeah.
Unless they're both present and then priority goes to the aldehyde, generally because the aldehyde can start at locant 1. But here, the aldehyde can't even start at locant 1. It's not in the chain. It's not in the ring.
Which make the, in my opinion, like when I'm saying this, it would make the longest carbon chain just 1 carbon. Because that's where the highest priority group is.
Yes. So I would have maybe called this 3-oxocyclohexyl methanal. You make the cyclohexanone ring a substituent of methanal. So a 1-carbon chain, methanal, with a substituent that is cyclohexyl that has a ketone, oxo, at position 3 from where the cyclohexyl attaches. I would have called this 3-oxocyclohexyl methanal. Or I would have called it 3-carbaldehyde cyclohexanone. I feel like either of those would have been better because you make one of them a true substituent of methanal, or you make the larger parent chain. So this is an example I would never want to give you guys because I don't think that it agrees with intuition. And nomenclature, I think, should agree with intuition. The rules that I've just given you guys, they're systematic, and the ones that I try to emphasize, they're meaningful. They help you avoid misidentifying a structural isomer. They remove confusion. I don't think that this removes confusion. Anyways, you guys notice the functional group we didn't really talk about at all? The functional group that doesn't even show up in here as the principal functional group. You guys don't see it? Actually, the cyanide is in here, but cyanide is actually called a nitrile. And so as a substituent, you have cyano, but as a suffix, it's called nitrile. We will talk about nitriles too, but I don't have you guys name them quite as often. What functional group we had no examples of? Yeah, the benzene ring. So transition into nomenclature of aromatic rings. So first of all, let's recognize that aromatic rings are not a principal functional group. They're not even listed next to alkenes, alkynes, and alkenes and alkanes. They do show up as a suffix. They're called, I'm sorry, I didn't mean suffix. Yeah. They do show up as a prefix. They're called phenyl. If you guys have ever seen phenyl abbreviated in a carbon chain, then you'll often, or if you've seen an aromatic ring abbreviated in a carbon chain, you'll see that it's abbreviated as pH. And do you guys notice something about the suffix that's within the term phenyl? It's that little YL that says this is not a parent chain, this is a substituent. So this molecule here, this could be called 2-phenyl pentane. And there's an aromatic ring. And I could expand that aromatic ring. There's no reason I don't have to draw it. But, wow, why would you want to? It's a lot easier to just write pH. We're going to do a lot of reactions in the next unit that involve aromatic rings. Some of them I am happy to allow you to abbreviate as pH. Others actually involve the aromatic ring, and so we can't abbreviate them. Or they have the aromatic ring with something else coming off of it, and so we don't want to shorthand it to pH. We need to show the structural connection. But I'll point those things out as they show up. Now let's say that you have a relatively small carbon chain coming off of your aromatic ring. That can make the benzene ring a parent chain. And most of them just end with benzene. But we can also add suffixes. So we can have things like benz aldehyde. And the aldehyde acts as a suffix. It tells me I've got a benzene ring, and then off of it I've got an aldehyde. During the break, I was showing you guys some of these example problems that are on this page, and how sometimes complex molecules will use something like this, cyclohexane carbaldehyde. We've got something like that, benzaldehyde. We're also going to see things like benzoic acid. Essentially, benz acts as the root, and then I don't even need a true suffix. I can just modify it right away. But then there are some common names as well. Some names that don't necessarily imply benzene right away. Instead, I want to look first at small-ish substituents. Ooh, you guys are going to get good at drawing benzene rings. I'll clarify this later, but if you guys want to, you don't have to draw all of these alternating double bonds. You can draw circles. You maybe have seen that before looking at materials online. Some aromatic rings are drawn with circles inside of them. It can help you abbreviate it, but I'll explain why it's not always a good method. There's a couple more that I want to put up. Yeah, I think that's good. Each of these compounds has an IUPAC name, something systematic that avoids any confusion. Some of them have a common name as well. A common name which you have to basically memorize. It's a common name that doesn't explain itself. So I'll go through and I'll list them in two different colors. This first molecule as an IUPAC name. I think you guys could name this. Can I hear it? Benzyl. Benzylene. How does the methyl get implied there?
This is how it is.
I want an IUPAC name. I want something systematic that avoids confusion. So if I call it benzylene, I have no idea there's a methyl group.
One methyl,
Vinyl or vinyl. A vinyl group.
phenyl.
Phenyl. Oh, okay. Well, phenyl is a substituent name.
And
So if I call it methylphenyl, there's no root. Methylbenzene. Now, you are onto something, Roth. We could call it phenylmethane. But we won't. We'll call it methylbenzene. Now, I don't have to describe that the methyl is at position 1, because where else would it be? It's on the ring, so it's at a position. But there is a common name for this, which is toluene. Toluene.
So with benzene rings, does it not matter, like, because parent chains are usually the ones with the most carbons, with benzene rings, does it not matter? Because, like, if this one, technically the benzene ring would be the parent chain, because it's got more in the pentane one. So is it like, you can kind of pick, or what's...
Yep.
Yeah? Okay.
No, that is a good way to say it. You can kind of pick which one you want to be the parent chain. It is odd that even though benzene has 6 carbons, it's not always considered the parent chain. I think you would agree that 2-phenylpentane is actually a nicer name for this molecule. The other way we'd have to name this, if the aromatic ring is the primary substituent, we'd have to name this as the primary, or sorry, benzene ring is the root parent chain. If this was a substituent, then it would be a 1, 2, 3, 4 carbon substituent with a methyl coming off at position 1. So this would be 1-methyl-butyl. I guess I might not even need that. Benzene, which doesn't look as pretty.
Yeah.
And it actually feels less intuitive.
Yeah, so it's okay to just, even though it's not the parent, like,
Yeah.
should be the parent chain.
Yeah.
Okay.
It kind of deviates from the rules of what should be the parent. Okay, what about my next one? How could I name this with benzene as the parent chain? What would be the IUPAC name? I think I heard a couple of things. I think I heard hydroxybenzene, which would be the IUPAC name. But I did hear benzenol, because alcohols show up in the suffix as OL, and it looks like benzene ends with alkene, and so it looks like I could just take off the E and put in that OL. As it turns out, the common name for this compound is phenol, where we do put the OL at the end, but we don't call it benzenol, we call it phenol. You know what the most challenging thing about calling that molecule phenol is? It sounds a lot like phenyl, which is the substituent name. So you say phenyl and phenol, it's hard to distinguish them. Okay, now this next one. I know we didn't talk about the names for amines, but if you look at this list, amines are substituents called amino. So the IUPAC name here is aminobenzene. What do you think the common name is?
This one, aniline.
Nice. How'd you know that?
It's like the only one I remembered from the textbook.
This is aniline. Not to be confused with alanine. Alanine is an amino acid. Aniline is this common benzene substituent. All right, now we've got this next group. As a 2-carbon alkene substituent, this group is called vinyl. So this is vinyl benzene, which is distinct from allyl. Allyl benzene would have an additional sp3 hybridized carbon in between. And this has a common name as well. I think it's going to sound more familiar to you than you'd believe. This is styrene, which is a principal component in what everyday item? Styrofoam. When you polymerize styrene, when you get one of those alkenes to bond to the next one, to bond to the next one, to bond to the next one, it creates this polymer carbon chain with a bunch of benzene rings coming off of it, and that's styrofoam. This group doesn't have a common name. It's only systematic. This one is nitrobenzene. The next one has no common name. This is only bromobenzene. This molecule on top does have an IUPAC and a common name. Can you guess its IUPAC name? How do you indicate that both the methyl group and the oxygen are attached in the order of oxygen to methyl? It is an ether, but we won't say that in the name. We won't say ether. Actually, we could. A functional class name would be methyl phenyl ether, which describes the two sides connected to the oxygen. But I need to describe that there's both a methyl group and an oxygen group. So I call it methoxy. Methoxybenzene. And the common name for this is anisole, which I think is related to the spice. Is there a spice, anisole?
There's no table of this?
Yep, I think your textbook should have this table. Or if not a table, it's kind of a list. Disclosure, I don't really care for you to memorize these common names. Toluene is one that I think we'll talk about enough that you might see it, but the other ones, I'm not so interested in. I just want you to be aware that they go by different names. The last one, I don't think this has a common name either. This is sulfonylbenzene. This little SO3H group is a sulfonyl group. Okay. Any questions on that so far? Pretty straightforward. Now, I want to get into two substituents. And first, we're going to look at these two drawings. You'll need to pay careful attention to where the double bonds are. Or if you don't want to pay careful attention to where the double bonds are, then you just need to shift where you draw the two methyl groups. Are these the exact same molecule, structural isomers, or can they be interconverted? Is there maybe some equilibrium between these? How would you distinguish these two by their names?
No different.
You think they're different? Not different? Would you agree that here, my two methyl groups are connected to the carbons that share a pi bond? And here, my two methyl groups are connected to two carbons that do not share a pi bond. And if we were to try and describe the difference, we could use something similar to alkenes, where I start at an alkene carbon and I number through the alkene in order to get to the next position. In this case, I could start at the first methyl group, which is the start of an alkene, or the pi bond anyways, not an alkene. And I could number this 1, 2 going through the double bond and call it 1,2-dimethylbenzene. But here, if I start at the same position, in order to count through the pi bond, I have to go an opposite way and call this 1,5-dimethylbenzene. So is it true that 1,2-dimethylbenzene and 1,5-dimethylbenzene, I'm sorry, not 5. Math is a little hard. 1,6-dimethylbenzene. So is it true that 1,2-dimethylbenzene and 1,6-dimethylbenzene are different compounds? Do they have different physical properties? Do they have different chemical properties? We learned that more substituted pi bonds are more stable and less substituted pi bonds are less stable. But if you isolate either of these compounds, you'll find that neither of them exist, because the placement of the pi bonds is kind of artificial. These are resonance forms of each other. So I have this versus sign because we weren't sure what their relationship was, but I'm going to erase that now and fill in. These are resonance. So with aromatic rings, we don't have to count through the double bond. These are both 1,2-dimethylbenzene. But this term 1,dimethylbenzene is also given a common name, which is xylene. And so we can have 1,2-dimethylbenzene, 1,2-xylene. We can have 1,3-xylene. We can have 1,4-xylene. But with these two substituent chains, we also don't have to use numbers. Because we kind of ran into that issue of, do I go this way or do I go that way? Do I have to count through the pi bond or can I not count through the pi bond? As it turns out, we can just take that structural relationship of being 1, 2, and we can give it a different name, which is ortho. And so this molecule can be called 1,2-dimethylbenzene, or it can be called orthoxylene. So ortho, sometimes abbreviated as O, is a 1-2 relationship of our substituents. Meta, abbreviated M, is a 1-3 relationship. And para, P, is a 1,4 relationship. Do you guys know the like the international name for acetaminophen? It's called paracetamol. And just based on that, you can recognize why paracetamol has para in its name. It has a substituent and another substituent that are 1,4 to each other. They're directly opposite. This really only applies to 2 substituent benzene rings. You cannot apply orthometapara to anything else. And then oh yeah, you know what? There were some other ones that I wanted to put up here. Sorry. Ones that we will see quite often. But these don't really have a IUPAC versus a common name. This is just benzoic acid and benzaldehyde. I think I already wrote it up for you, but I wanted you to see them. Benzaldehyde. So now when we start taking these common substituents and we start combining them onto our benzene ring, we can do one of 2 things. We can list the 2 substituents alphabetically and just place their relationship in front, or we can place the relationship in front and name one of the substituents and then give the common name for the other. I'm abbreviating the CH3 there as Me for methyl. This compound can be called ortho bromomethyl benzene, which is IUPAC. Or it can be called ortho bromo toluene. Last week, those of you in lab worked with this starting reagent, which has both a sulfonyl group and an amino group. The amino group makes the molecule aniline. So the systematic name here would be para-amino sulfonyl benzene. The common name would be para-sulfanylic acid. I don't like that quite as much either, but it emphasizes the fact that the sulfonyl group is acidic. And how do you see that there's the amino group? How do you know that aniline is in there? Anylic, sulfanylic. Yeah, we've got aniline, A-N-A-L, anylic. But it kind of combines them. We can actually do the same thing with toluene and benzoic acid. So let's look at this compound. Systematic name, IUPAC name. I don't really have a way of saying benzoic acid other than benzoic acid. So these are meta-methyl benzoic acid. It tells me that I have benzoic acid and I have a methyl group and that they are meta to one another. But the systematic name would be meta-toluic acid. Toluic implies toluene. And the ic acid implies the carboxylic acid. Kind of distinct from sulfuric acid, implying not a carboxylic acid, but a sulfon. What I want you guys to pay attention to are these groups, ortho, meta, para. Those are the ones we're going to use quite a bit. These common names, this is not something I anticipate you guys knowing, but I do want you to be aware that those names kind of get squished together for, I don't know why, but it's common. You'll see it, especially if you're in the lab this semester. Okay, any questions so far? We'll do some practice problems when we come back in tomorrow and segue into understanding more about this circle. Why do we represent it with that? I've taken you guys a bit over, so thank you for your time. I'll see you tomorrow.